Okay, very excited to present our work on how to regulate algorithmic decisions when they are too complex to be fully described today. The context to our project is that we increasingly rely on prediction algorithms in high-stakes screening decisions. And in many of those decisions, there may be incentive conflicts in play between agent building a prediction function and a principal overseeing their use. So just to give you 3 examples here, we could think of medical testing where an insurance company worries that a hospital overpredicts risk in order to perform too many costly tests. In hiring, we could worry that an employer wants a certain fairness of their job offers by a hiring agency, but the preferences by the hiring agency are not necessarily aligned. And in lending, which will be the leading example today, because this is where I can show you some empirical example, you could worry about a financial regulator who worries about disparate impact or model risk, where a lender predicts risk and based on that takes credit approval decisions. And the regulator cares, for example, about the fairness of the allocation or may be worried that there may be systematic risk. Now, on the one hand, the move to automated rules in this area, and specifically the use of complex machine learning, actually allows for a systematic and even ex-ante review relative to decisions taken by humans. But at the same time, the move to very complex machine learning methods also means that it is complicated by the complexity of algorithm, and we often end up with complex functions that are hard to describe and cannot be fully understood by the regulator or human decision makers. And so in this context, what we're doing is we're using a principal agent framework in order to ask and answer the question how we can effectively mitigate incentive conflicts if the algorithms that are used in a prediction task are too complex to be fully described. And the starting point to the talk today is a principal agent model where we assume that the complexity of the algorithm means that the agent cannot fully describe the algorithm to the principal. So we assume that it's not possible for the agent to fully hand over all details of the algorithm. So there would then be a first policy option that we allow the principal to have, which is the principal could simply restrict the agent to use only simple algorithms that can actually be fully described. So we're thinking here about credit approval. So think of this as saying, I know that you could use a neural network that may have some advantages in terms of precision of predicting default, but you really have to use a simple logic model because that's what I completely understand. A second policy option that we specifically consider in our talk today that instead would be that the principal allows the agent to use a complex model, but requires the agent to provide some simple description or explanation of algorithm behavior in terms of key drivers of that behavior. So for example, asking for the key variables that are important for a credit decision. And tools that can do that are already widely available and actually used in fintech and are used in this area, which very much motivated our study here. But they're often based on mathematical axioms of what it means to describe an algorithm. So one famous way of doing that I've illustrated here is using Shapley values to basically assign the importance to the different variables that go into a prediction function and say I predict default and I use some credit file data for that and say one of the variables there is whether you have a mortgage on your home. Now, if I want to use that variable, then these explainer tools would basically tell me how important that individual variable is. I could then inspect the important variables and based on that decide whether I think that this algorithm is conformal. Now, the problem is that a lot of the axioms underlying exactly those kinds of explainability tools are not necessarily motivated in economic terms. So they're not necessarily motivated by using them in a specific way, but they're often motivated by mathematical axioms underlying their mechanics. And so what we do instead here is we start with a principal agent model and make precise and justify why we should care about explanations of complex machine learning models in this model, where explainability is not an end in itself. So I don't necessarily care about explaining as an end in itself, but I instead care about explainability in order to take good policy decisions and specifically regulate well. And what I will argue in a specific example in the following slides and what we lay out in a more general model in the paper is that just doing ex-ante restrictions to simple functions is generally inefficient. And specifically, we can generally do better by doing regulation based on algorithmic audits that use simple representations that are feasible of the complex algorithm. However, we also show that these explanations are not all equally helpful and that it makes sense to use explanations that are specific to the context that we look at. We then empirically demonstrate that results matter specifically for credit underwriting. And we also have a companion product with Finreg Lab, which is a DC-based nonprofit in this space, to evaluate how diagnostic tools that are already available address regulatory requirements, and how both those tools and the regulatory requirements should evolve if you want to ensure the fair provision of credit and safe provision of credit. And so this, of course, related to a fast-growing literature that goes across multiple fields, including mechanism design and the incentive conflicts in algorithmic design. The one that I want to highlight here is a very active literature in computer science on algorithmic explainability, relative to which we try to derive the properties of optimal explainers from economic theory rather than from mathematical axioms that describe their mechanics. So I'm now going to lay out the basic model, and I will then very quickly switch to a very specific example in order to translate those ideas for the talk today. So we assume that an agent takes a prediction, classification, or assignment decision. So basically searches for some function that maps some characteristics X, some features X to some decision F, and has data available with a label Y, an outcome Y, and features X, and does so in order to obtain low loss on new samples. So in order to translate this into my specific setup that I will think through today, I'm now specifically going to consider a lender where that function F is a credit scoring or loan approval decision, where the outcome is whether somebody repays a loan, and the available features are those that would be available in a credit file that a lender has available. And I then consider, for illustration, two loss functions. Like one would be maybe I come up with a credit score, and I want that credit score is close to the probability of the default, either by using logistic regression and making such transformation, or just by using squared loss, which I will use today for simplicity. So in that case, my goal is to find a credit score that predicts default well. A second type of loss that you can think about would be the loss from loan misallocation, where you either incur a cost if you give somebody credit who doesn't repay their loan, or you incur a cost if you don't give somebody credit who would have repaid it. I assume that the lender receives a training signal. So think about this, the lender gets access to some existing data about the distribution of the repayment probabilities and the covariates jointly, uses this signal in order to come up with a function, in this case, a loan approval or credit scoring decision. But that choice is overseen by a regulator who maximizes welfare, which may be different from lender utility. So specifically in the talk today, going to assume the lender minimizes loss or maximizes, in this case, this utility function, which is negative loss, while the regulator may have different welfare function in mind. So to give you two concrete examples, one would be disparate impact, where the firm, so the lender, cares about getting a precise credit score, and the regulator cares about precise credit score that is not too different between a majority and minority group in the data. And a second example would be one of a risk preference, where again, the lender minimizes loss, while the regulator minimizes worst case loss across different states of the economy, and would, for example, be worried that in a downturn, there would be excess defaults. Here, I'm now going to focus on this risk preference example. And in that example, I'm going to talk through our main framework to then lay out the main ideas of our paper. So we assume that there's a game between the principal, who's the regulator here, and the agent, who is the lender, and that proceeds in 4 stages. The first stage is a rule setting stage, where the regulator sets the rules of the game. I'm going to be more precise about it in a moment, what these rules are. The second is a training stage, where the lender learns the relationship, in this case, between 2 covariates, just to keep it very simple, 2 binary covariates, and the probability of default, and then takes the decision of how to estimate the credit score. So in this specific example, I have to talk this slide through in a little bit detail. I assume that there is a function that relates 2 variables that are both binary to an outcome. The ones that I've chosen here are past default, which is usually very indicative of future default. And the second one is whether the applicant has a home equity loan of credit. I'm going to go over in a moment why I think that's an interesting variable in this context. And then I also allow for the interaction. So in other words, this is a fully complex function. And when I was talking about like complex machine learning, just for the sake of the talk today, just think of it as a function with those 4 variables. And then the lender chooses a simple, another, not simple, but like such function that also maps those to an outcome. And I assume specifically that there are different states of the economy and that some of those coefficients, specifically the intercept and the effect of home equity loan on credit, on default can vary. Specifically, home equity loan of credit, we think of a good sign in a good economy. At least this is what I will use for this illustration. But we may actually see it as a bad sign in a bad economy because it means that somebody has already taken out the credit. But in a good economy, it could be a good sign because it means somebody has a collateral. So this is variables where I assume that this probability will be higher, the probability of repayment will be higher in a good economy, and it will be lower in a bad economy. Okay, in the audit stage, the regulator then performs an audit where the regulator has only limited information available about that function f hat that the lender would like to use in order to assign credit. And then in the outcome stage, the consequences of deploying that function and payoffs are realized, where I assume that if the regulator fails the lender in the audit stage, they get minus negative infinity utility. So meaning that in this case, the regulator can enforce certain constraints through the audit. Okay, I'm now going to go over the main challenge that we isolate in this problem, or that we add to this very standard model, which is we assume that there's an information constraint where the regulator cannot fully understand the complexity or the full function that the lender chooses. And to do this in a very stylized way here, I assume that this full function, which is characterized by 4 parameters, I can only understand a 2-dimensional characterization of that, so 2-dimensional linear projection of that on one of the covariates and an intercept. And the main idea of our paper is that the moment that we explain something complex in very simple terms, so in this case, we project a 4-dimensional function onto 2-dimensional space, there's a consequential choice to be made about which information we preserve, because we necessarily have to destroy some information by our assumption that the full function is too complex to understand. And the way that I write this here is I think of the left as the full function, so varying by both x1 and x2. And I could, in principle, use 2 different projections, either on x1, which is on in the middle here, or on x2, which is on the right. So the lender then observes in the first step this distribution, and we are now thinking about different ways in which the regulator could constrain their choice. And I'm going to now go through these choices, and in going through these choices, come back to the idea of an explainer. So as a reminder of the setting I'm looking at here, I'm thinking about a probability of default that is a function of 2 variables, where some of those coefficients may vary between a good and a bad state of the economy. The lender just cares about minimizing expected risk, where I assume that there is some very low probability bad state of the economy, while the regulator cares about worst case risk across those states. Now that means that the lender and the regulator prefer different variables after learning, different functions after learning about the distribution. Specifically, the lender just optimizes for the average. The regulator prefers choices that are optimized for worst case. And now the specific form of that is not really important here. What is important is translates into different ways in which the regulator can constrain the firm. So specifically, the first one would just be to be totally laissez-faire and to not put any constraints on the choices by the lender. In this case, we would get a maximal distorted choice where the lender would simply choose their first best, which I've here denoted by those alpha bar and gamma bar to denote the choices that are optimized for the average. A second choice that we would have would be an ex-ante restrictions to simple functions. So I could tell you you're only allowed to use a simple function, which here would be, for example, you're only allowed to use a function that varies with x1, but not one that varies with x2 or the interaction. And in that case, we eliminate misalignment because we force the agent to choose a function that as a regulator can fully understand, but at the cost of destroying a lot of flexibility and thereby not finding a function that fits the underlying economic relationship particularly well. So now comes the idea that instead I'm using an explainer that I put as an exposed constraint, where ex ante I leave you to choose any function. So practically, I allow you to use a neural net, but I constrain the explanation in terms of a simple projection onto a few variables. And here I have choices. So I could first do the thing which in this simple example that I didn't go over in much detail would represent the one that explains most of the variation in the prediction function f hat of x. In this case, that would be using only the projection on the variable x1. And that would maximize the overall information I maintain. However, here it wouldn't help us that much because the source of misalignment is a very specific variable. It was this home equity line of credit, which I call variable x2. And that difference between the lender's choice and the regulator's preferred choice is not detectable by the specific explainer. So instead, what I could have done here, of course, in this very stylized toy example, I could have instead used the other variable, which is exactly the one that is the source of misalignment. And I could have said, I instead care about an explanation that may not explain the overall function as well as it can, but it is as related as it can to the source of misalignment. And so in this case here, that would have been to regress on the other variable, which would have achieved the first best. So just to summarize the main idea, as we explain very complex models in simple forms, where the neural net I kind of encapsulated in the example here by basically a fully interacted variable model with two variables, then as we explain it in simple ways, we have a choice to be made. There's a choice to be made about how we explain it. And the main takeaway of our paper is that from an economic perspective, that matters. And so it matters to define explainability as a means to an end, and then use explainers that are specifically targeted. And so in order to drive that point home, let me now choose a slightly different example for the last minute of my talk here. And specifically, I'm now thinking about not the case of a risk preference, but instead the case of disparate impact, where the lender minimizes prediction loss, while the regulator cares about prediction loss plus some disparate impact. So cares about not producing a function that has extended differences between a majority-minority group. And the reason why I mentioned this is we implemented this in credit scoring data to show how important these things are in practice. And so what we do here is we assume there's a best prediction explainer, which is basically an explainer that is optimized for explaining the first order behavior of our predictions as well as possible, which we fit using a lasso regression here. And second, a targeted explainer that specifically focuses instead on explaining a function in terms of those covariates that are particularly related to minority status in our data. And the audit constraint is then basically that the function is desirable on those restricted functions. And just to very quickly show you the results that I realize I won't have enough time to go into detail. So what we show, and I have to apologize because I realized that I cut out the slide, exactly the slide with the empirical results, is that basically the explainer that goes after the explanation that is particularly related to minority status is better able to align the preferences and to minimize DI. And it does so by basically picking out those variables that allow me to reduce the disparate impact, which is our measure of fairness here, improve disparate impact as much as possible. So I'm at time, so let me just quickly summarize here. So our starting point was that the move from to automated rules, where we take screening decisions using machine learning, allows for systematic scrutiny, but complexity of those decisions means that we face a decision of how to restrict and explain those complex functions when we regulate them. In a broader context, we have tools available to explain complex machine learning, but interpretability and transparency are often defined as ends of itself rather than means to an end, which we do in our model. So we are asking, therefore, how we can regulate black box algorithms that are too complex to be described completely. And the answer we give from a perspective of principal agent model is that we should use targeted explainer that target the specific source of misalignment. And this is related to a broader agenda of evaluating available explainer tools in financial regulation, of which we have recently published a report. So I put a link here. So thanks so much for your attention. I'm happy to take a few questions.
Okay, yeah, thanks for the interesting talk. I was curious if this also lets you think about sort of syntactic categories of explanation, right? So some of your explanations involve projecting out a variable, others involve simpler functional forms. So these would be sort of, right, sort of distinguished on sort of the syntactic style of them rather than the sort of motivation for them.
I think that's a great question. So the way that I think of it on a very, very high level is that no matter which kind of motivation for the explanation you have and which type of explanation you have, whether this is a specific projection or it is motivated in a different way, say you want to give a causal explanation or describe the process by which something was fitted, to the degree that it fits into a framework where we think of it as basically being simple language for something that in principle can be very complex, we always face an information compression. And so we want to think about kind of what basically when we compress information, which dimensions do we want to preserve and which dimensions are we okay with parting, and then the information we should preserve should be related to the source of misalignment. So I think that's the main takeaway, which I think on that very high level is very robust. But we have thought about it in practice mainly as basically exposed explainers that project in some way or the other effectively the complex function on a simpler space. But I do think that it would be interesting to expand that in other ways of explaining, including using other process or some more causal explanations.